Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 9, Lesson 9 on the equations of circles. We're now going to enter a portion of this particular unit where we get ourselves out of the Euclidean plane and we go into the coordinate plane and we look at some things having to do with circles in the coordinate plane. Namely, in this lesson and the next lesson, we're going to be looking at how we can describe the points on a circle that are located in the coordinate plane with an equation. So let's jump right into it. Circles centered at the origin. Now circles can exist in the coordinate plane. Obviously they can, right? Just as lines can. We can write equations that describe all the xy pairs that lie on a circle. We will first look at how to write the equation of a circle whose center is at the origin. All right? And that's a good place to start, right? Those are going to be the simplest of circles. Let's take a look at exercise number 1. A portion of a circle whose center is at the origin, 0, 0, and with a radius of 10 is shown graphed below. The circle contains the point 6, 8. Another arbitrary point on the circle has been plotted at x, y. All right, before we do letter A, I just kind of want to mention this arbitrary point business, all right? So in other words, I've put just some kind of random point right there. And that's so that later on we can generalize whatever we're going to do with this specific point. So there's a specific point, 6, 8, that lies on the circle. And then we're going to be taking a look at just some sort of like arbitrary point that lies on the circle. Now let's look at letter A. To the right, redraw the right triangle from the image that has 6, 8 as one of its vertices. Label the leg lengths that you know. All right, so in other words, I just want to take this particular right triangle, all right, and I want to reproduce it in this space right here. Let's do that together. That's easy enough, right? So we've got our nice right triangle, kind of looks like this. We've got this point up here at 6, 8. And of course, the whole point of that, right, is that this has a length of 6 and this has a length of 8. All right, very, very simple. Those are the legs that I know. Now let's take a look at letter B. Find the length of the hypotenuse of the right triangle from A using the Pythagorean theorem. Awesome. So why don't you go ahead and do that, right? Using this right triangle, find the length of that hypotenuse just using the Pythagorean theorem. Take a moment to do that. All right, let's do it. Simple enough. 6 squared plus 8 squared is equal to c squared. 36 plus 64 is equal to c squared. 36 plus 64 is 100. That's equal to c squared. Take the square root of both sides, and c is equal to 10. All right, so the hypotenuse of that right triangle is equal to 10. Now, letter C. Why does your answer from B make sense given this circle? All right, why does this have to be the case? Why does this make sense? Pause the video right now. Well, it makes sense because, right, this length is simply the length of the radius. Right? It had to be 10. If it was anything but 10, then that couldn't have been the radius, right? So what I'm going to say is the hypotenuse of the right triangle is a radii or a radius of the circle, so must be 10 units. All right, we were told it was 10. Right, you can also tell it's 10 because, right, if it's centered at the origin, we can go up here and see it intersects at a y-intercept of 10. It's got an x-intercept of 10 here. If we had completed the picture over here, it would be at negative 10, and it would also be at negative 10 down there. All right, but again, it's obvious, right? It had to be 10 because that thing is a radius. Now, letter D. Draw the right triangle below that has the arbitrary point x, y labeled on it. Write down the length of its hypotenuse. Right, so now, right, we've got this particular triangle. We're going to just draw that thing out. All right, here's that point, x comma y instead of 6 comma 8. We know this is x. We know this is y. And because its hypotenuse is a radius of the circle, its hypotenuse must be equal to 10. Finally, letter E. Write an equation based on the Pythagorean theorem that relates x, y, and the radius of this circle. Well, that's a piece of cake, right? This is my A, this is my B, this is my C. So if I've got a squared plus b squared equals c squared, that gets replaced by x squared plus y squared equals 10 squared. And I think I'll take that just one step further and then leave it. I'm going to say x squared plus y squared equals 100. And that is the equation of this circle, right? And that means that I could take any point, like x equals 2. I could plug it in here and I could solve for the two y values where x was equal to 2, right? This equation gives me all points that lie on this particular circle, or it describes all the points that lie on the circle. In other words, any point that lies on this circle, when I square the x value and I square the y value and I add them together, I have to get 100, just like the point 6 comma 8, right? 6 squared is 36, 8 squared is 64, 36 plus 64 is 100. And every point that lies on this particular circle will have that equation. But really, what is that equation? It's just the Pythagorean theorem, where the x and the y are the a and the b of the Pythagorean theorem, and the radius is the c, right? It's the hypotenuse. All right, so let's summarize that. Equations of circles with centers at the origin. All x comma y points on a circle whose center is at the origin, 0, 0, and whose radius is r, can be described by x squared plus y squared equals r squared. Now again, I can't emphasize enough that all this is literally the Pythagorean theorem. A squared plus b squared equals c squared, except a is x, b is y, and c is the radius of the circle. Exercise number 2. A circle has an equation x squared plus y squared equals 36. What is the radius of this circle? All right, well, this is simple enough, right? Whenever we have a circle of the form x squared plus y squared equals r squared, this number is the radius squared. So the radius squared is 36, which means the radius must be the positive square root of 36, which means the radius must be equal to 6. It's real simple. That is always r squared. Now letter B, a little bit more challenging. Does the point 5 comma 3 lie in this circle? Justify. Well, pause the video now and see if you can figure out whether the point 5 comma 3 would lie on this circle. Well, this is no different than every question you've ever been given, where you've got the equation of a line and you're asked whether or not a particular point lies on that line. What do? You take that point, you substitute it into the equation. If the equation is true, the point lies on that curve, whether it's a line, a circle, or anything else. If the equation is false, then it doesn't. That is literally the connection between equations and their graphs. So it's very simple. I'm going to just put 5 in for x, whoops, and I'm going to try to write a 2 there. 5 squared, 3 squared equals, maybe put a little question mark above it, 36. I'll get 25 plus 9 equals, again, question mark 36. 25 and 9 is 34. 34 is most certainly not 36, and so the answer is no, right? The only points that will lie on this circle are ones where when we square the x and we square the y and add them together, we get 36, and that's not the case with the point 5 comma 3. All right, simple enough. Now, circles not centered at the origin. Now, of course, circles don't have to have centers at the origin. It's very convenient when they do, but they don't have to. Those that do not will have equations that can be directly derived from the distance formula, which, recall back from Unit 5, itself comes directly from the Pythagorean theorem, all right? So recall the distance formula, right? The distance between points x1, y1 and x2, y2 is d equals the square root of x2 minus x1 squared plus y2 minus y1 squared, the square root. Or if I've squared both sides, the distance squared equals x2 minus x1 squared plus y2 minus y1 squared. Again, I really want you to understand this. The distance formula is very important. Whenever we used it back in coordinate geometry proofs, we almost always used it in this form. But it really is just the Pythagorean theorem. It's when I subtract the two x's, right, that gives me the length of one leg of the right triangle. Subtract the two y's, that gives me the length of the vertical of the right triangle, right? And then the distance between them, right, that was the hypotenuse of the right triangle. That's just the Pythagorean theorem again. And that will now allow us to come up with the equation of a circle not centered at the origin. Let's take a look at exercise number 3. Consider a circle with a center at 4, 2 and a radius of 5. Letter A. Show that the points 8, 5 and 1, -2 must both lie in the circle. Well, let's be very clear, right? Don't worry about the like anything that we've talked about with equations of circles so far, right? The plain fact is a point will only lie on this circle if the distance that the point is away from the center is equal to 5. Simple, right? That's it. So if I want to show that these points lie on this circle, I have to show that the distance between both of these points and that particular point is equal to 5. Let's do it with 8, 5, and then we'll have you do it with 1, -2. All right, so I'm just going to use the distance formula. Simple enough. Okay, and again, I'm trying to find the distance between that point and the center. That's going to be 8 minus 4 squared plus 5 minus 2 squared. All right, 8 minus 4 is 4. So I'll have 4 squared, 5 minus 2 is 3. That's 3 squared. That'll be 16 plus 9. That's the square root of 25, and that's 5. So yes, since the point 8, 5 lies 5 units away from the point 4, 2, it must lie on the circle that has that as its center and that as its radius. Why don't you go ahead and use the distance formula to show that the point 1, -2 must also lie on this circle. All right, let's do it. So I'm going to maybe start it over here. Again, we're just trying to find the distance now between that, whoops, let's try that again, that point and the center. 1 minus 4 squared plus -2 minus 2 squared. 1 minus 4 is -3. We've got some negatives to deal with here. -2 minus 2 is -4. -3 squared is 9. -4 squared is 16. So I'm going to get the square root of 25, and that's equal to 5 again. So both of those 2 points must lie on this circle because they are both 5 units away from the center. All right, awesome. Now let's take a look at letter B. Let's come up with the equation for this circle. Letter B, given that x, y is an arbitrary point on this circle, write an equation for the distance this point is away from the center of the circle. Rearrange this equation so it contains no square roots. All right, so in other words, I now want to use the distance formula, but instead of having, 4, 2 here and, 1, -2 here, or whatever it was, right? I just have x, y here. So the distance in this case is going to be the square root of x minus 4 squared plus y minus 2 squared. All right? Now, of course, you might say, well, why didn't you do 4 minus x squared and 2 minus y squared? And you totally could. But in general, when the arbitrary point is x, y, and the center is whatever, known, then you always do the arbitrary point minus the coordinates of the center instead of the coordinates of the center minus the arbitrary point. But I want to be very clear, it really wouldn't make a difference, but this is the standard way of doing it. Now, the thing is, if this point is on this circle, then the distance is actually equal to 5. All right? Notice it says rearrange this equation so that it contains no square root. Well, to do that, all we're going to do is we're just going to square both sides, therefore effectively canceling out the square root, and I get x minus 4 squared plus y minus 2 squared is equal to 25. And that is the equation of that circle. right? Now, by the way, notice how similar this is to the equation of a circle centered at the origin, right? The equation of a circle centered at the origin was x squared plus y squared is equal to r squared, right? In this case, what we have is we have x minus the coordinate of the center of the circle, the x coordinate of the center of the circle before we've squared it, y minus its center coordinate squared equals r squared. So it's very, very similar to this. We just have to shift it, right, to take into account that the center is no longer at 0, 0. So, to summarize, equations of circles. A circle with a radius of r and a center at x sub c, y sub c has an equation given by x minus x sub c squared plus y minus y sub c squared equals r squared. Okay, so again, in this case, right, these two things aren't going to be variables, right? They are going to be the coordinates of the center. And those coordinates are going to be subtracted because this is just the distance formula, right? Or it's just the Pythagorean theorem, right? Where this is the horizontal leg, that's subtraction. This is the vertical leg, that's subtraction. We square them both, and we get then the square of the hypotenuse, which is still the radius of the circle. Wow. Let's take a look at exercise number 4. For each equation shown below, state the center and radius of the circle it describes. All right, so letter A is easy. I've got x minus 5 squared plus y minus 2 squared is equal to 36. And again, right, what we've said is that we're going to subtract off, right, the coordinates of the center of the circle. In other words, right, the center, which I'll just use as C, is going to be at 5, 2. Right? I've subtracted the 5 from the x, the 2 from the y, 5, 2, and that will always be the radius squared. So the radius squared is 36, which means the radius must be 6. All right. Oh, I like these. These are easy, right? Now let's take a look at letter B. X plus 4 squared plus y minus 1 squared is equal to 100. Ah, this then gets a little confusing. Here I've got x plus 4 squared, but I need to be subtracting off the center of the circle, not adding it on. So what do I do if there's an addition there? Well, keep in mind, right, that x plus 4 can be thought of as x minus negative 4. Right? So x plus 4 squared is the same as x minus negative 4 squared, right? And then the y minus 1 is okay, in which case the center is at negative 4, 1, and the radius squared is equal to 100, which means the radius must be equal to 10. Now, you might have already started to pick something up here, right? Which is that if I look inside of the parentheses and I sort of see a, if you will, a negative 5 there, then it's a positive 5 there, a negative 2 there, it's a positive 2 there. A positive 4 here becomes a negative 4 there, and a negative 1 there becomes a positive 1 there. It's almost similar to when we had that point slope form of a line, right? Y minus y1 equals m times x minus x1, right? And when we end up subtracting the negatives, we end up getting those positives. This really is the same thing. We're really taking a circle centered at the origin, and then we're shifting it, right? So that we get centers that aren't at the origin. Let's take a look at letter C. X squared plus y minus 3 squared equals 1. Well, this one looks particularly confusing because I'm not subtracting anything from x. And that's really the key, right? I'm not subtracting anything from x. And if you really want it to look like up here, you could always rewrite this as x minus 0 squared plus y minus 3 squared is equal to 1. Right? And once you do that, again, if you're following this form, it gets to be pretty easy. The center is then at 0, 3, and the radius ends up being the square root of 1, which means the radius is just 1. Okay. See how much you get this by finishing off the last 3. Once you have this, these are very quick. Identify the center and the radius of each one of those circles. All right, here we go. Well, again, this one's kind of a combination of B and C. Here, my center is going to be at -4, 0, and my radius is going to be the square root of 16, which is just 4. All right. Here, my center is actually at 0, 0, and my radius is the square root of 9, which is just equal to 3. And finally, here we've got kind of a double negative almost going. My center is at -2, -5, and my radius is the square root of 81, which is equal to 9. We'll just circle both of them. All right, that's it. So when you're given a circle in this particular form, it should be very, very easy to identify both its center and its radius. Let's get a little bit more work with this in one last problem. All right, so one more time, right? Equations of circles, right? They have the form x minus x sub c squared plus y minus y sub c squared equals r squared. So exercise number 5. A circle has a center at the point 6, -2 and passes through the point 10, 3. Write its equation. All right, so this is what I always tell students in a situation like this, and this is not unusual, right? Now, the problems that are easier are when we're given the equation and we're asked for its center and its radius. But sometimes we're given the center and we're given one other point that it passes through and we want its equation. So the first thing I do is I say write down anything you can write down. And given that we know what the center is, right, I can write the following down. X minus 6 quantity squared plus y minus -2 quantity squared is equal to r squared. All right. Now, this I might want to clean up a little bit, right? So I'm going to have x minus 6 squared plus y plus 2 squared is equal to r squared. Now, in order to finish this, I got to have a number sitting over here, whatever it is. But the cool part is now I can take that point and I can substitute it in for x and y and I can figure out the rest. Now, let's take a look at that, right? So I'm now going to take this point and I'm going to substitute it in. We can always do that. Even if that doesn't look like the word substitute, I can substitute it in and I'll get 10 minus 6 squared plus 3 plus 2 squared is equal to r squared. 10 minus 6 is 4. 3 plus 2 is 5. 4 squared is 16. 5 squared is 25. And I'll get 41 is equal to r squared. Now, 41 is not the nicest number. The radius is certainly the square root of 41. But there's no actual need to write down r equals the square root of 41. If you'd like to, please go ahead, be my guest, that's fine. But the plain fact is the equation of the circle doesn't have r in it, it has r squared in it, right? And the principle of substitution now says wherever I see an r squared, I can put in 41, right? So ultimately, I'm just going to put 41 up here, and that's going to give me my final equation, x minus 6 squared plus y plus 2 squared is equal to 41. Now again, there's nothing wrong with taking the square root, getting the square root of 41, and then squaring it and getting 41. But it seems a little redundant. It's sort of like, well, how do I come in the house? Well, I'm going to open the door and leave the house and then open the door and come back in, right? Can I do that? Sure, it's one way of getting into the house. But if I'm in the house already, why go through all the trouble? That's all. Anyhow, let's summarize, right? Equations of circles in the coordinate plane basically boil down to the Pythagorean theorem / the distance formula, right? That's what they're all about. Something squared plus something squared equals something squared. And if that doesn't ring like the Pythagorean theorem, I don't know what would. Now, you've got the very specialized case where you have circles centered at the origin, and oftentimes we do deal with circles that are just centered at the origin. X squared plus y squared equals r squared. Clean, easy. It's almost like it's a line that goes through the origin, right? It's like got no y-intercept, okay? Or it's got a y-intercept of 0. On the other hand, circles that are centered somewhere other than the origin look like x minus the center x-coordinate squared plus y minus the y-coordinate of the center squared equals r squared. And again, all that is the distance formula or the Pythagorean theorem between some arbitrary point on the circle and the center. That's it. Get some practice on this on tonight's homework. We're going to work more with equations of circles in the next lesson, but we're also going to have to bring in something from last year, completing the square. But we'll talk about that in the next lesson. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.